well, our next talk is by Joachim Breitner. Something weird. And he's going to be presenting his functional Perl on more fixed points, appropriate for our second talk after we heard an introduction to fixed points.
Thank you. I like Haskell. A not very bold thing to say in this crowd, but you still might be wondering, why do I like Haskell? And there are many reasons, this crowd being one of them. But one particular reason I like Haskell is I like purity. And purity is great because you don't have to worry about side effects, everything is nicely compositional, and you can do this equational reasoning. Equational reasoning in particular is, I think, an amazing thing to do when you have to deal with a programming language compared to all these languages. But you can't do it. But what does purity mean, actually? Like, what is the essence of purity? It was actually hard to find a formal definition that kind of describes purity, but even informally, I tried to boil it down to like one small, minimal slogan, what purity is. And I came up with this. So I'm sure you all recognize the various LaTeX fonts. So the left one is the code font, the right one is the math font, and the middle one is the prose font. So purity means equations are equalities. You write down equations in your program, and the thing on the left and the thing on the right, they are equal. And this is what unlocks all this power of equational reasoning and treating this like math. And Haskell is great because it's a pure language. Haskell is also great because it's a lazy language, and I like laziness. Now, again, there are many reasons to like laziness. Obviously, the thing about unused expressions not being evaluated, so that's clear. You probably heard Simon point out that laziness is what keeps the language honest. In a non-lazy language, you might be more tempted to give up purity, but in a lazy one, you really don't want to, and this helps. So since I like purity, I like laziness. But there are more reasons to like laziness, and the one that I want to talk about here is laziness is what allows us to have recursive definitions. I claim you can't have recursive definitions in a non-lazy language. So let me give an example for something that's even mutually recursive. So the typical example is odd and even being defined in terms of each other, and this is how it might look like. And here we have some mutual recursion. Now I sense a little confusion in the audience because this doesn't quite look like the Haskell, not even with all of GHG's current extensions. This is C code for those of you who actually haven't seen C before. And a little bit tongue-in-cheek, I claim that C is a lazy language because you can have recursive definitions and you can write the top definition there and you can make sense of it even though you haven't defined everything it's being composed of. And it actually only really matters what you put on the right-hand side at some point later, which is in a way laziness, or at least non-strictness if you want to be pedantic, but for this talk, let's just call it laziness. So C is a lazy language. Still, I think Haskell is great because it's lazy, and it's lazy in a way that C isn't. And this means laziness is a spectrum. So you have languages like C where some things are lazy, namely function definitions. It's pretty hard to imagine a language where the function definition isn't lazy in that way. You would have to try hard, but that doesn't change the fact. But then in Haskell, of course, many more things are lazy. Many data structures are lazy, many functions are lazy, and you can do more things in recursive equations. You can do these knot tying tricks where you define something that is using itself in a way that the whole thing still works and makes sense. The prominent example certainly is Fibonacci numbers as an infinite stream. I want to take you along and look at this concrete, relatively practical application of this knot tying in Haskell. So we have graphs. I represent them here as maps from integers to their successors as lists. And then I want to define the reflexive transitive closure of the graph. So for each node, what other nodes can I reach? And I solve this by writing a local definition where I have a map that maps each vertex to the set of vertices you can reach from that vertex. And I basically write down the specification as an equation. It's the last line where I say, well, reachable from a node V is, well, V itself, and then all the things reachable from nodes that are adjacent to V. And this is a recursive definition. it can only work because we have laziness. And let's see if it actually works. So I load this code in GHCI, and I run the function on a simple graph, 3 nodes, 2 edges, and it returns a graph. And it's probably hard to see if this is really the reflexive tensor closure, so I also put it on the slide here. So this works. This is the kind of program I use to try to impress programmers that haven't experienced the beauty of Haskell yet. And I think this is great. This is a declarative programming at its best. Unless the person I'm trying to impress is clever and asks me to add one little edge to this graph. And if then I have to do this. So if I'm looking at my code and I add this little edge and I'm already fearing what will happen, it doesn't work. So it does something, it prints a little bit, but it doesn't calculate the result. And that is disappointing. I have a nice declarative specification of the problem. It describes the solution that I want. Why do I not get it? So let's see, why does it actually go wrong? So we have this map structure that we're kind of using laziness, using this knot tying trick, so maybe that breaks. And to better understand this problem, we can reach back to what I said earlier. Haskell is great because of purity and equational reasoning. And we can start unrolling things to see what's happening. So this is the expression that failed in the function, and now I'll do these equational steps. I'll fast forward to the interesting point. So we inline the function, the g is only used once. We map a function over its data structure, so we can move the function to the values. We give name to the values. We inline the function f. There's a list comprehension over known list, and we're here. And now something interesting happens. We have not fully evaluated the program yet, but we know enough about this map reaches that we can look up into it. We don't know what S1, S2, S3 are going to be, but we know that looking up 2 in this map will give set S2. So we can resolve these lookups at the bottom, and now something magic happened. The recursive definition for reaches has disappeared. We've tied the knot, we've pulled on the strings, and we got straight line code. I like this analogy. So our use of a lazy map in a knot tying way was not the problem that made this not work. The problem is still here. It's the recursive definition of these sets. And I said earlier that you need laziness in order to have a recursive definition. So maybe the problem why this doesn't work is that this is not lazy enough. And indeed, if we look at the data structure API for sets, probably in the docs somewhere, or maybe it's not even spelled out, but these functions are too strict. The set library in Haskell, the insert on the unions and so on, they need to know their argument completely before they can do something. They're not lazy, and therefore you can't use them in a recursive equation. And that makes me sad. And I was wondering, could it be that this just works? Can we write that API in a lazy way so recursive definitions work? And I believe you cannot in like normal standard Haskell. But I'm not using normal standard Haskell, I'm using GHC. And GHC has all these things that go beyond, in particular, unsafePerformIO, which is basically, you can do anything you want, just be careful not to break things. And this is what I tried. So there's a rectef library, it has a module that has pretty much the same API that the original set. It has also a function to convert back to normal sets. And these operations are lazy. And we can try. So, one slide more. So this is the code that we wrote before. The API was essentially the same. So it's rather straightforward to just plug in the different types and the different functions, project out at the end. And I can now try this. So yeah, this is still running, oh my God. So let's load this other implementation. It's the code from the slide you just saw. Of course, the acyclic graph just works as before. But now I can run the cyclic graph and it works. Which is always anticlimactic. It's just like, okay, yeah, no, there's something there, but hey, it works. But people were wrinkling their forehead when I said unsafePerformIO. This is like dangerous territory. So the question is this kosher? Can I really do that without breaking all the beauty of Haskell, of programming with Haskell? And the question really is this still pure? And I think it is, and I think there's a very simple argument why it's still pure. And it boils down to what I said earlier, like purity means equations are equalities. With my library, if you write an equation like the top one, which is taken from the code that we just saw, it will do something, but at the end it will assign values to these variables so that this equation becomes an equality for these finite sets. And this means equation of reasoning still works, this means it's still pure. So this is a very short argument why, in this case, it is okay what we're doing. It doesn't really matter how we're doing it, and I will not too much dwell on the implementation in this talk, but rather the effect it has on the language, which is okay. Of course, sets are a particularly nice example for a domain where we can do this, because with sets and monotone functions, there always is a unique least solution that we want to compute, and with a bit more restrictions on the API, we actually always get one. It's always computable. So this works really nicely. The broader takeaway is that I think there are many examples where this should work. So when you have, like in a language like Haskell that likes to be declarative and pure and lazy, and you can do things with recursive equations, I think whenever you have a domain where you have this property, that any finite equation, any finite set of equations has a unique, most desirable solution, and you have a way of computing it maybe even, then that should just work as equations. You should be able to write down the equations and get them as a very, very shallow DSL, so to say. And this means we can now look at the spectrum of laziness and go further than the Haskell that we know. So with my library, which you could think of as a language extension, everything is using unsafePerformIO is in a way a language extension. There's now also sets and Booleans that you can use in recursive equations, and there are more domains that are quite obvious, other ones more tricky but actually more interesting. I think grammars might be useful to explore. We have these nice parser combinators, and they have this property that you write equations and they describe a solution, but they tend to fall apart if you use left recursion, and it doesn't have to be that way, at least not from an entitled user point of view. And I really think that there's something to explore where we can gain something. So the first thing we gain, of course, is we can now solve more problems using this nice, declarative, pure style. We saw the graphs. Previously, we could only do it for acyclic graphs, and suddenly we can do it for cyclic graphs as well. It's also, like this declarative thing is important. If you were to solve the problem of reflexive transitive closure for cyclic graphs in normal Haskell, if you do it naively, you're starting to mix declaration of your solution and the solution algorithm. You would have to probably have some local function that iterates through the graph and keeps track of what it has seen. And you want to keep that separate if you like abstraction. But if you don't like abstraction, you wouldn't be using Haskell anyway. Of course, there are ways of keeping that separate in Haskell. We just saw one in the talk before. So you could either try to shove all the bookkeeping in a monad and declare it in monadic style and then query the results. And that works, but I always feel sad when I have a nice pure function and I have to, for some reason, now make it monadic. It makes the syntax heavier and you see less what's really going on. You could also use fixpoint operators, fixpoint combinators. Maybe the fixpoint combinators can be filled with fixpoint operators. That is certainly a valid approach as well. It works really great for like a single recursive equation. You just put it in fixed and that's fine. It gets more and more hairy the more complicated your things are. If you have multiple equations, you have to tuple them up. If the number of equations or values that you want to get out is not statically known, you have to deal with maps. If you want to make it handle heterogeneous equations, so a set of equations where some equations are in sets and some are in Booleans, but they are connected, then a very general fixed point combinator for that seems to be an interesting puzzle to come up with. And where it really breaks down, I think, is when the set of equations you're collecting in order to pass them to the combinator, when this happens in not one local lexicographic space. So imagine you're traversing a syntax tree in a programming language, what we do every day, I guess, and every node you learn new equations, you define new variables that you want to solve for, and you want to solve the whole thing together. Then this mismatch between the the structure of the code that creates the equations and the structure of the equations itself, which is one global thing, really becomes tedious. And this was a lot of words, but maybe the best way of expressing the benefit from this approach is we do have a fixed point combinator in Haskell to define recursive functions, the data function.fix. But we're not using it to define recursive functions, we're using let bindings or top-level bindings because it is the most convenient way to describe a set of recursive equations. So why only do it for Haskell functions? Why not for other domains as well? So this is why we should maybe look into this style of programming. There are reasons, or there are caveats that I should point out, of course, as well. So first of all, it's not always applicable. You really need this property that for a given set of equations, you have a unique, most desirable solution so that you preserve the purity. And I wouldn't want to give up purity for notational convenience. So this is important. Then I didn't say much about the implementation. I will not say much about the implementation, but it relies heavily on sharing. So you need to have this property that you define a finite number of equations and not accidentally an infinite number of equations that you never see the end of when you're trying to solve them. So anything, so in this way, working with this library is just about as mind-bending as working with other knot-tying tricks, whether like the ones you may use for memorization or dynamic programming. So it's not completely easy, but it's doable. It's something that Haskell people tend to at least enjoy writing blog posts about. I don't know how much you want to do it in production. And then because termination now becomes critical for the whole thing to work, we do change the equational theory of Haskell. Now, I stand by my statement that it's still pure, but there are equational contextual equivalences of Haskell beyond just purity. For example, lambda lifting is not observable in Haskell normally, but with this library it becomes, because it breaks share. Now, a transformation like lambda lifting is already a somewhat dangerous transformation because it can dramatically, meaning asymptotically, change the performance of your program if you lose sharing. So this is reassuring to me because it means the compiler will not just do that willy-nilly. But it is one of the problems, certainly, of this approach. Right, so this was the talk variant of this thing. The paper is actually rather different, so let me advertise the paper a little bit. There's a larger use case which comes from program analysis. There's a nice connection to the previous talk, I guess, where I really wanted to write my program analysis without having to encode where I do the fixed pointing and all these things. And then, of course, how do I actually do this unsafePerformIO thing? I think there's a neat idea where I'm using thunk identity implicitly as the identity for nodes in my graph. It's not even reified into a data structure. It just becomes this graph on the heap where the values propagate, and this works rather nicely. Of course, once you have unsafePerformIO, you really have to worry a lot about reentrancy problems. So even if you have basically means you don't necessarily have threats, but you still have all the problems of concurrent programming. And these needed to be addressed and solved. Space leaks become an issue. I can't do all equations. Let x equal x is annoying because there's no function involved where I can do magic using unsafePerformIO. So this is what you get when you do these things as like a library and not just put it in a new programming language. Like related work like DataFun, which would be the closest inspiration, I guess. It looked like there should be a denotational semantics for the whole thing, very easily. I mean, Haskell has the nice denotational semantic. This fixed point finding on sets has a nice denotational semantics. But somehow the combination is rather tricky. There's some non-continuity happening. So this is work in progress. I have a draft I can share. I would be very happy to show that to people who think this should be easy and tell me how to do it. And of course, the library's package, you can play around with it. So let me just put on the two maybe main takeaways of this talk, and I'm looking forward to your questions.
Thank you very much. We have lots of time for questions. both here and online.
Yeah, that's what I get for being over time every time I practice, and then I'm speeding up every time, and then of course, once I do the real one, it's plenty of time. But looking forward for this discussion.
Thanks. Can you draw any similarities to Plotkin's parallel OR? Because it lets you evaluate two things without evaluating the first one. If the second one gives you the answer first. So your union you could try to implement by using a parallel OR if Haskell had such a thing.
So is the question whether if we had parallel OR, we could do this without using unsafePerformIO?
Because that doesn't change the notational semantics.
That's an interest. So I guess the reason why you, I'm not sure, because the reason you can't do this in plain Haskell naively is you can find that a value is in a set. Like imagine you do the sets as like lazy lists, and if a value is in the list, you can look it up and find it in finite time. But as you keep doing this looping, you will never know that something is not in there. So I'm not sure if the parallel OR thing.
Well, you know it's not there only if it evaluates to a value telling you it's not there, right? But if it keeps on computing something, then yeah, you loop, but you will loop anyway, I think.
Well, not here.
Not here?
I mean, that's the point. I can write this recursive equation that if it would just try to implement that as like lists, it wouldn't loop.
No, but you would end up in the same place. So you do this. Okay, maybe it's offline. I think.
Yeah. But it might be interesting. Yeah. Thanks.
Okay, we have a question from online. Michael Adams asks about left recursion. So is that something that you can do today in your system, or is that future work? And how far future?
That is future work. I haven't tried it seriously yet, so I don't know how far. It shouldn't be hard, but how can I say that when I haven't tried it?
Famous last words.
Yes, definitely.
Yes. Another question here, and please introduce yourself.
This is Yi-Hong. We have some email exchange before. So for example, if I want to bring my own lattice to a framework, what should I do? Do I need to start from scratch? Is there a principal way from your framework to support these extensions of other lattices?
So the library itself is slightly modular. So it takes an imperative propagator network, or I might make it more general, an imperative library that it can be in I/O, where you can declare variables, you can declare equations, and you can ask for solutions. And if you have that, no matter how you implement it, you can use the generic unsafePerformIO based wrapper to wrap it up in a pure API. And as long as your library has certain properties, which I haven't spelled out completely, but it's roughly what I said. Every set of equations needs to have a unique solution, no matter in which order you declare things, no matter in which order you query things, then you should get a pure result out.
So it's a more generic framework than just RSet, and it's support.
Yeah. So the library at the moment supports recursive sets and recursive Booleans. It has a different implementation for solving them. For the Booleans, it uses something smarter, where you only propagate when something goes from false to true. For sets, it's rather naive. Could be a smarter implementation, and you could add your own like solvers into this mix.
Thanks.
So I'm Simon Peyton-Jones. Your this thing you have on the slide here is very attractive, right, as a programming story. But somehow there must be a bit more to it than that, right? Like you've got to have, don't you have to have some notion of a monotonic thing? So there's some kind of ascending train. You got to reach the fixed point. If I just write, let x equal x times x. Well, that has maybe one solution if x is of type nat, but you're probably not going to find it, because I could write the solution of polynomial equations. So as a programmer, how am I going to know the boundary of what's possible and what's not? And do I have to be in some type class or what? Yeah.
So indeed, and what I try to do in the implementation is to keep separate the idea of I have a domain where I can solve, and I'm wrapping it up purely. So the overall statement is whenever you have a domain where all equations have solutions and you can solve them in an imperative way, you can also have a pure API. So now you ask, for example, natural numbers and addition. So when you add something new to this, like a new domain, you have to, of course, design the API or choose the API so that this property holds. So for example, for set, we don't have all the functions. We only have those functions that are monotone as the user. And this by construction, we always have a solution. So if you were to define like recursively definable natural numbers ordered by like the normal order, then you would have addition and multiplication, but you wouldn't have subtraction. But then it would still work. But it's true, it's not going to be the case that now suddenly everything you can just write in a recursive equation and it will have a solution. You get smaller APIs that guarantee that you have a solution.
So, but my question is still, as a programmer, how do I know whether I can use your technique? Because I've got your library. Does your library just provide a fixed set of domains and that's
Yes.
it? You know.
Yeah.
So, and if I want a different domain, I'm out of luck. I need to apply to you for a new domain. Is that?
So I guess it depends on which programmer you are. That if you're like the end user who just wants to have a pure API and do these things, then yes, you only get a fixed API.
Okay.
If you're like, I forgot the name already, but the person who just asked about extending it, then you can use the components of my library to extend it and provide more APIs.
I see.
But then there are some safety conditions you have to do to ensure yourself. Then it's not completely like then you have to do something to make sure it still has the properties.
Okay, we have time for maybe one more question. Yeah.
Can you go back to the slide where you have the unique solution? Yeah. Could you weaken this a little bit to just have a unique least fixed point, or?
Right. Sometimes when I was reading it, I snuck in the term a unique most preferred solution.
Yeah.
So of course, if I write something like let s equals this is one of these recursive equations. I can make it bigger, sorry. And of course, this equation has many solutions. Any set that happens to have 2023 in it is a solution, but usually we don't want these. So we usually have a notion of what's most preferred. So in lattices, ideally, hopefully, is the least one, then you can solve for it. I said most preferred because this is not restricted to fixed point analysis. You could have a solver that does something completely different, like linear programming in convex domains or whatever. As long as there's a unique solution you will get, no matter how you set up your set of equations, then I think this technique applies.
So I'm not quite sure how you exactly implement it, but it will always find a kind of least fixed point, or it's not doing anything beyond that, right?
So for sets and Booleans, it will always find it. The API happens to be just, I'm not showing slides. The API for sets that we have is in a way that there's going to be a solution and it's going to be finite, so it will be representable as finite sets and you can find it. There's an open question whether we would, for example, want to allow set.map. Set.map is interesting because it is a monotone function, so you will have a least solution in terms of sets, but not necessarily of finite sets. In other words, if I were to add set.map to this to API I provide, you could write equations they're not productive. They will not be productive always, so it's still pure. And that's why I think it might be okay. Haskell programs are used to non-termination. I kept it out for now because nobody asked for it. But there's a little wriggle room, like do we want to allow APIs where not every set of equation has a solution, or only has a solution when you also add like a non-termination on top.
Okay, thank you.
Okay, let's thank Joachim again. So that concludes this session. and we have a half-hour break, and then returning in the grand ballroom reports from various contests. Thank you all.